Hello! Today we're going to continue talking about writing simple assembly for the x86-64 instruction set architecture. In part 1, we discussed registers, the move instruction, and addressing modes. Part 2 went over arithmetic and logic instructions. Now in part 3, we'll cover conditional and control flow instructions, and part 4 will deal with procedures. So our discussion today aims to continue your orientation toward understanding and writing assembly source code for the x86-64 ISA. Here we'll introduce the assembly instructions you need to understand branch structures like if-else and loops. Recall that a program is a sequence of machine instructions and data created by compiling high-level source and assembling assembly language source into object code that is linked to create the program. The format of machine instructions is defined by the ISA, which provides a one-to-one mapping to readable assembly instructions. This includes the opcodes and the operands. So a given line of assembly corresponds to exactly one machine instruction and vice versa. Remember that these are the 16 general-purpose registers of the x86-64 architecture. The mnemonic used for a register depends on whether the instruction should use the entire quad word of 8 bytes, double word of 4 bytes, or even a word or byte. We're now going to look at instructions that make use of registers outside of the general-purpose architectural register file. Control flow instructions modify the program counter, which keeps track of the next instruction to fetch in the program. On x86-64, the program counter is called the instruction pointer and resides in the special purpose RIP register. Conditional instructions rely on the condition codes, which are also stored in a special purpose register called eFlags. These codes are modified by instructions, including arithmetic and logic, and by compare and test instructions, which we'll discuss today. We're only going to worry about these 4 condition codes for basic assembly: the carry flag or CF, zero flag or ZF, sign flag or SF, and overflow flag or OF. There are other condition codes, such as the parity flag, that we will ignore. The condition codes are modified by arithmetic based on the result value. So an add, for example, sets the carry flag if the most significant bit has a carryout, which can be used to detect overflow of unsigned addition. The zero flag is set if the addition resulted in the value 0, and the sign flag is set if the most significant bit is 1, which is the sign bit in 2's complement representation. The overflow flag is set in case of a signed overflow condition, which can be detected in 2's complement when addition of 2 numbers with the same sign has a result with the opposite sign. The compare instruction does a subtraction of its 2 arguments and sets the condition codes based on the result, but it does not write that result anywhere. Note the ordering of source 2 and source 1 here, which reflects the AT&T syntax. The main use of compare is to check equality and inequality conditions of 2 different operands. We'll look at some examples later. The test instruction similarly does a bitwise AND of its 2 operands and sets the condition codes according to the result, which is also discarded. The test instruction is most often used to check equality and inequality conditions of a single variable compared with 0. Again, we'll look at some examples later. The set instructions are used to clear or set a byte-addressed register based on the condition codes. When we talk about setting something, that means making it 1, and clearing means making it 0. These instructions can be used to put the results of equality and inequality tests or comparisons into a register variable. Set E for set equal will set the least significant bit if the 0 flag is set. ZF is set after a compare instruction with 2 equal operands. The opposite condition is set any for set not equal, which will set the operand if the 0 flag is cleared, and vice versa. This sets for set signed and set not signed do the same with the sign flag. This is used to check if the result was negative or not. Then there are several set instructions that deal with inequalities. These are used after a compare instruction. Set G for set greater checks if the comparison indicates source 2 is greater than source 1 with 2's complement signed numbers. The logic to figure out these conditions is shown, and you should think through why these work on your own. Similarly, set GE does set if greater than or equal, and then we have the other directions, set L for set less than, and set LE for set less than or equal. Then we have two set conditions for unsigned comparisons. The set A instruction stands for set above, which essentially does set if greater with unsigned numbers. And set B does set below, or set if less than with unsigned. There are more set instructions, including set above equal and set below equal, but these are the mainly useful ones. After a set instruction, you will usually need to also clear the upper 7 bytes of the register so that the register holds only the result of the set instruction. The MoveZBL instruction does this. It stands for Move 0 Extend Byte to Long. Note that this is a 32-bit instruction, but it will set the upper 32 bits to 0 as well. So the destination operand of the set instruction can be used as the source operand of MoveZBL with the 32-bit mnemonic for the same register as the destination. For example, setQ%AL would be followed by MoveZBL%AL%EAX to zero out the rest of the RAX register. The primary use of the condition codes is to accomplish conditional jumps, which are sometimes called branches. A jump instruction encodes a jump target as an operand that it writes into the RIP to change the address for the next fetched instruction. The unconditional jump instruction, JMP, always jumps to the target. Generally speaking, conditional branches will execute a compare or test instruction that will set the condition codes on purpose. Then one of the conditional jump instructions is used based on the condition for branching. The JE instruction means jump equal, and it jumps if the 0 flag is set, which it is after a compare instruction between two identical values. The JNE instruction is jump not equal, which jumps if the 0 flag is not set, that is, it is clear, which happens after a compare instruction with two different values. The JS instruction jumps if the sign flag is set, so it jumps based on a negative result of test or compare. The JNS does jump not sign, which jumps if the sign flag is not set. By now, this should be feeling familiar. Indeed, there are corresponding jump instructions for each of the set instructions we just examined. So here is the jump if greater than, and the jump if greater than or equal to. Then there is jump if less than, and jump if less than or equal to. Finally, for unsigned comparisons, we can do jump above for unsigned greater than, and jump below for unsigned less than. Now we have the basic tools we need to construct branches and loops. Remember this example that calculates an absolute value without using a conditional statement? Let's quickly walk through it again before we look at a version using conditionals. The first line of C code becomes two instructions. One to move the argument to a temporary register, and then shift the sign bit through the entire register. Then the input parameter is added to the mask before XORing with the mask, putting the result into RAX to return it. The function returns with the return value in RAX. Here's a little more direct way to find an absolute value using a conditional expression. This shows us a few new instructions. Let's walk through this example. The first thing done is to make a copy of the input argument V and put it in the return value register RAX. The test instruction does bitwise AND of its two operands and sets the condition codes for sign and 0. The condition we're checking here is for a negative signed integer. So the test instruction ANDs V with itself. So the sign flag will be set if V is negative and cleared if V is non-negative. The 0 flag will be set if V is 0 and cleared if V is non-zero. We'll take a closer look at each of those. Now that we tested V, we need to check the specific condition of interest. Looking at the C code, we see it as a ternary operator. If you're not familiar with this operator, it encodes an if-else condition in one line. The if block follows the question mark, and the else block follows the colon. So if v is less than 0, the statement should result in the negative unsigned long of v, and if v is greater than or equal to 0, the statement should result in v. The condition used in the assembly here is the less than inequality. So the jump variant chosen is JS, which stands for jump if sign set. In other words, jump if negative. This means the program execution will jump if v is negative. From the C code, that means jumping to the code that follows the question mark, which will return the negation of the unsigned long cast of v. The jump target is .L2, which is an assembler label that identifies the address of the instruction following the L2 label. So if v is negative, the RIP will be written with the address of the instruction located at L2. If v is not negative, the RIP will be advanced to the address of the next straight line instruction in the program as usual. The next instruction in the program is what follows the colon, which is to return v. This instruction happens to also be labeled, but for now the L1 label is ignored. Let's follow the non-jump case first. We sometimes call this the fall-through case because the program falls through the jump instead of hopping. This case is simple. Return v. Since we put v into RAX earlier, it is ready to return. So the fall-through code is just a ret instruction. Now for the jump case. Jumping to L2 sets the RIP to the address of the first instruction in the assembly code after the label. You'll usually see this written either on the same line as the label, or sometimes the label is written on a line by itself with the instruction on the next line. The label itself does not take up any space in the program. Adding a new line after the label does not change the instruction of the jump target. Anyway, the first instruction after the label is the negation of RAX, which holds the copy of v. This one operand instruction overwrites its source with its result. So v is less than 0, and we write the negative of it into RAX. Now RAX holds the positive of v, that is its absolute value. The next line of assembly is an unconditional jump back to the instruction at the L1 label. So now that label comes into play. In general, when you have an if-else type of condition, you'll have two jumps. One jump to go over the fall-through code, and then another jump to rejoin the control flow after the paths down both if and else sides finish. In this case, the fall-through code itself is where the two paths meet. Now the execution of ret will return the negation of v because that was written into RAX by the code at L2. Another instruction in x86-64 is the conditional move. This instruction uses the condition codes to determine whether or not to complete a move. The idea is to translate code that conditionally moves one variable into another. This can be generalized to convert code that assigns a variable in an if-else construct into a straight line version with a conditional move at the end. The form is typically to put the result of the else path into the register you want the variable to be in, such as RAX. The other path is put into a temporary register, such as RDX. So both sides get calculated, and then the condition is tested to decide whether to overwrite RAX with RDX or not. After the cmove, the RAX holds the value you want based on the test outcome. Sometimes the order of RAX and RDX will be swapped, and the test will be inverted. For example, cmove could be replaced by cmoveNE. The advantage of conditional moves is that they can get rid of branch statements, which can be expensive in modern processors, as we will discover in a few weeks. The disadvantage is that both paths get computed, so there is some waste. And you can't use it if either path has a side effect in it, such as updating a different variable other than the left-hand side of the assignment. At any rate, we can generate code using a conditional move for this function. Here we generate the than portion. We put negative v into the return value register RAX. Here's the test condition. We don't have to do anything for the else part since v is already in RDI. But since we have the then part in RAX, we need to invert the test condition. So if the sign bit is not set, that is, if V is not negative, we'll move V into the RAX register. Otherwise, we still have negative V in RAX, and we know it is positive. And we'll return the right answer. Before we discuss loops, let's look at some simple C language transformations that get control flow code closer to the assembly equivalent. This will make our comparisons between high level and assembly easier. Here is an if-else version of our ABS function. We can transform this to a Goto version by using the logic of the test and using it to jump to the then part. If the jump isn't taken, then the else part becomes the fall-through code. Now we can generate assembly that looks almost identical to the C code. When transforming if-else conditionals to Goto statements, you can also complement or invert the test condition and then switch the order of the then and else blocks to make them in the same order as the original. We'll start loops with the do-while loop. This is the easiest to translate to assembly. Here's a function that implements popcount, an operation to count the number of 1 bits. This is also known as the Hamming weight. This is a fairly straightforward loop-based implementation. It initializes the result with 0, and then iteratively masks all but the least significant bits of the argument x, and adds that into the result. This adds a 1 if the least significant bit is a 1 and 0 otherwise. Then the argument gets shifted right by 1 bit. This repeats until the argument is 0, then we're done and return the result. We can translate this loop into a Goto-based version first, before we look at the assembly version. The do turns into a jump target, which we label loop. The while x becomes a Goto back to loop if x. The generated assembly is similar to the Goto structure. It starts by clearing RAX to hold the result. Remember that the upper bits are zeroed automatically when using the 32-bit registers. The start of the loop body is labeled .L2. The loop body contains 4 assembly statements to move the input variable to a temporary RDX register, AND it with 1, and add the result to the RAX result. Then the input register RDI is shifted right by 1. When the immediate is omitted, it is assumed to be a 1 in the shift instruction. The loop body ends with the jump back to L2 if the condition code for the 0 flag is not set, which is a side effect of the shift instruction. After the loop ends, there's this rep-ret. You can ignore the rep. It is an artifact of a hardware bug that makes ret after a jump not work right in certain processors. The fix for hardware bugs tends to be made in the compiler because you can't really patch and update hardware. So in general, a do-while loop can be converted to this Goto version with a label at the start of the loop body, and then an if of the test that will jump back to the start of the loop body if true. Conversion of this to assembly is relatively straightforward, depending on how complex the test is. One way to convert a while loop is to keep the structure but invert the test. The loop label comes before an if statement to check for the inverted test condition. If the test is not true, the loop is exited. Otherwise, the body of the loop is executed, and then an unconditional jump is taken back to the start of the loop. While loops are similar, since the condition needs to be checked at the start of the loop, another way to rewrite it, using Goto, is to first jump over the loop body to the test condition, then check the test, and jump back to the loop body if it's true, or else fall out of the loop. This is one way to convert a while loop to an equivalent version using Goto that generates code that is similar to the do-while loop. Here's another implementation of popcount using a while loop. Functionally, it is not much different from the do-while loop, except that it will not waste one execution of the loop body if x starts out equal to 0. The conversion to Goto shows that the while statement gets replaced by a Goto to the if statement after the loop body. Another way to translate a while loop is to first convert it to a do-while loop and then apply the Goto transformation. The trick is to make sure the loop body doesn't get executed the first time if the test condition isn't met. This is done by adding an if on the inverted test condition with a Goto to after the loop body. Then the loop body of a do-while loop can be used directly since the if statement guards entry to the loop. Last but not least, we have the for loop. Remember that a for loop consists of 4 components. The init statement always runs prior to the loop. The test statement runs prior to each loop body and breaks the loop if the test is false. The update statement runs at the end of every loop body. So a loop iteration is a test, body, and update. Here is a slightly different approach to writing popcount using a for loop. The init statement initializes 2 variables, r and I, to 0. The test statement checks if I is less than the wsize macro. Wsize is written as a pound-defined statement. This is a C preprocessor macro that will replace every instance of wsize in the C code with the calculation of 8 times size of int, which on the x86-64 is 8 times 4, or 32. The update statement increments I by 1. The body is a little different than before. It doesn't modify the input argument, but instead shifts it by the iterator variable I and bitwise ands with 1 that gets added to R. Let's walk through converting this to a Goto version. As an intermediate step, we'll convert the for loop to an equivalent while loop. The init statement comes before the loop because it always gets executed. The test statement becomes the test of the while because it gets checked before executing each loop iteration. The body goes in the usual place. The important thing here is to put the update statement after the loop body before the end of the loop. So we can convert the popcount for into a popcount while. The init statement will go first before the loop starts. Then we'll add the while statement with the test. We're going to put the update at the end of the body, so I left a little space here. And we add the loop body with the update at the end. From here, we could generate any of the while Goto transformations, and then the assembly code is straightforward. We can also generate a do-while loop from the for loop. In this case, we put the init statement before the inverted if test that decides if we should not do the first iteration. Then the loop body, followed by the update statement, and then the test again for the iteration. Now what's interesting here is that often the compiler can determine that that first inverted test passes for the initial conditions of the loop, such as this case where 0 is compared to less than 32. This is always true. So the compiler can optimize away this code when it generates the assembly. So this can be a little bit more efficient than a straightforward transformation or the for while transformation. So now you should have a basic grasp of assembly programming in x86-64 using arithmetic logic operations, jumps, and branches. Next time, we'll talk about procedure calls in the call stack.